here are the exams. I'll toss them out. No, I'll hand them out. But I want to show you what the results were. Those are all the scores on the left in decreasing order. The average was 70. Pretty big standard deviation. And you have to realize that you are the future generation of applied curing theorists. So you got to get it right, okay? It's a kind of obligation. You're carrying the torch. So I want you to think hard about these things. Some of the things I saw, some of you missed some things you should have known. Not all of you use the buy-in of points optimally, but I don't want to say I was disappointed with the performance, but I wasn't thrilled with it. It could have been better, but you see there's quite a range here. So let me hand these out to you folks, I'm sure you. By the way, the next homework is going to be to do the exam again. Don't hide from it, okay? So, first, John, these are in alphabetical order, okay? Rohit, Jeannie Kao, Zingyi Ku, Kao, okay. Sahil Dani, Boyan Ding, sorry about that. Matt Fiorello. Oh, well, I guess that's it, huh? Okay. Shulan Lee, Victor Lee, Lily Lin, Yoon Jae Long, Aditi Nakachandra, Adi, it's easy to pronounce it. Nicholas Nien, Andrew Polizotto, Derek Toshiba, Chloe, thank you. Joyce Tung, Alan Wu, and David Yang. It's pronounced Yang? Zhang, okay, good. Good job. So, again, I'll show you what the range was so you can position yourself there. Quite a spread. It'll be homework. Good. Okay. So let's review from last time now. In this lecture, last lecture, 11, we started with the method of stages due to Erlang. The idea is to extend beyond the exponential distribution so we can handle more. This being the exponential, we know how to handle that from chapter 3. Even beyond chapter 3, which is birth, death, we can still handle it by the inspection method. But here we've gone to the method of stages to go beyond the exponential. We're going to sums of exponentials in this form so that we introduce this notion of this R-stage Erlangian distribution, which is generated by having a customer pass through R stages of exponential. Essentially, that gives us a density that looks like this, and this is the family that Erlang has produced using this sequence of stages. And the first thing we did is we used this for the service time density in an exponential interval time, Erlangian service time, single server. This picture shows us what's going on. Customer comes in, they arrive. When they go into service, one customer at a time passes through these R stages, each at a rate R mu. And we recognize that the way to get around a two-dimensional state description, which would be the case of basically which stage of service the customer's in and how many customers there are. Rather, we said just let's count only stages of service in the system so that every one of these customers in the queue counts for all stages of service yet to be done on them. And so we defined this quantity J as the state variable, number of stages left. When there were K in the system and the customer in service in stage I, then the number of stages left is a full R for each of the people in Q, plus this many left for the guy in service if he's in stage I. Namely, it's this. This is the state diagram. We solve for the probability of finding so many stages in the system in equilibrium. Its Z transform is this. We wrote it down and solved for it. We found the Z transform looks like this. We inverted it and it looks like this. And we made the point that MER1 is a system whose density of number of stages is in fact basically a sum of geometrics. All these quantities are known, except we have to find these R roots of this denominator, which is the hard part. And in each case, depending upon what we have to find different roots. Okay. So this was the result. We did that. And then we said, let's extend it now in the opposite direction. Let's, in fact, create the system ERM1, namely exponential service, but now basically Erlangian into arrival times. Namely, we're going to use this as the inter-arrival time density. That's the Erlangian distribution with R stages. And the picture looks like this. If we have essentially K in the system, which means in the queue or in service, and we look at the people arriving, before they arrive, they're passing through a sequence of inter-arrival stages due to this density. So if the arrival customer is in stage I, how many stages of arrival has that person yet to go before they arrive? Let me say it differently, I'm sorry. How many stages of arrival have they passed through? Because I want the state variable to be how many stages of arrival are in the entire system, already, if you will, accomplished. Well, how many has this arriving customer already accomplished? He's in state I. How many? I minus 1. He hasn't finished this, and since each of these is an exponential, the fact that he's been there a while doesn't help him get out. It's memoryless. So that's what this I minus 1 is right here. And this R times K, if there's K in the system, each one of them has gone through R stages of service. And as Matt reminded me to remind you, there's only one customer in the arrival box at a time. And always one. It's never empty. As soon as somebody arrives, the next person starts immediately. So this person arrives here, someone pops in right here. There's always exactly one in the system, but at different stages of service, different stages of arrival. So again, the state variable is how many stages of arrival have been accomplished by the entire system, namely those who have already arrived, they've gone through R stages of arrival, plus this guy on the way in, and we have to keep track of him, he's gone through I, is in the I stage, he's accomplished I minus 1 stages. So that's the setup. Now we want to solve this system. Now I will warn you, the answer is simple, but the analysis is a beast. And they're going to take you through that torture just to show you what goes on. I don't expect you to repeat it, because the analysis is really quite interesting and something you see queuing theorists play around with quite a bit. Okay. So a moment. Okay, so let's draw a state diagram. What does the state diagram look like? We're going to have stages of arrival. They could be 0. How could there be 0 stages of arrival in the system? What's the physical situation if there's no stages in the system yet? Where are people? I want you to get the physics of this. Excuse me? Empty system, but what else? So there's no stages of arrival in the queue or in the server. Nobody's there. Empty. And there's no stages of accomplished arrival yet. So where is anybody else? Yes? Right, one in first state right here. Let me not use a pen. Let me use this thing. There's one person right there. He's not accomplished anything yet. So there's 0 stages of accomplished arrival. That's what this initial state is. Or we can have 1, 2, on up to, say, R plus 1. Let's go to J minus 1, J plus 1, and J plus R, dot, dot, dot. I ran out of space. So let's draw this diagram. Why am I being so careful drawing the diagram? Because what's the next step? The inspection method, which means to draw a circle around every state and write its equation. And the best way to do that is to draw the diagram so you can see what's going on. So let's do that. This looks fairly complicated, doesn't it? There's dot, 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 dot. And here as well. Okay. So, no stages of service, of arrival. What's the only thing that can happen from state 0? This guy can move from here to here. Then what happens to the state variable? You go from 0 stages of accomplished arrival to 1 stage of accomplished arrival. And at what rate is that happening? What's the rate of progress through each of these stages? It's at R lambda. So we're moving up at a rate R lambda. From state 1, you can go to state 2. In fact, all of the upward motions have that rate, R lambda. Okay, now let's see what happens from state 1. Where can you go? You can only go up. There's a single guy arriving through the arrival stages, but can you enter that state from anywhere above? Is there a way into this state 1 from some other state? And I'm making you think this through because I want you to be able to do this for yourself. What's this? Right, from R plus 1, you can have somebody essentially leave the system. And at what rate is somebody, that means there was, with R plus 1, what's the situation? Okay? There's one person in service, and there's a guy in stage 2. This guy already has his R stages of arrival. This guy in state 2 has already accomplished one of these, so that's an R plus 1. That's why we're here. And when this fellow leaves, he takes all his arrival stages with him. Okay? And so what rate are we going down here? Yes? You were really thinking of something else. Oh, but if you're in state R plus 1, then we know exactly what the situation is.
I was thinking about, like, because I was confused as to why the max number of states was not just R plus 1, and then I realized because you could have multiple in P itself, and then you have
More arrival stages that have been accomplished. That's why this thing goes on up to infinity. Okay, so again, I'm asking, what rate do you come down from R plus 1 to 1? What kind of a system is this? It's a pure exponential server at a rate mu. So clearly, this is a rate mu. Okay? And that means from state R, where can you go besides an increase? Where are you going to go coming down here? In state R, there's one person in the system. He's in service. And the arriving guy is in state 1. He's not accomplished anything yet. So the number of accomplished arrival stages, when there's one person here, he represents R stages of arrival he's accomplished. That's why we're in that state here. And the arriving customer is right here. Accomplished nothing. But coming down now, what can happen? Somebody can leave. This fella can leave. And when he leaves an empty system, again, at a rate mu. Nobody seems comfortable with this. Let's go a little further, okay? That means I can come into state 2 from state R plus 2 at a rate mu, etc. Now from R plus 1, of course, we can continue on up and continue on down. But let's look at the J situation. Let's look at state J. From state J, I can go up with a rate R lambda. I can go down at a rate mu. I'll go to J minus R. But what else can I do? How else can I get into state J? I can come in from below with a new state of arrival being passed. I can leave with a new state of arrival being passed. A service can be completed, and I go way down to J minus R. But how else can I get into state J? J plus R with what? A service. And where does it come from? It comes from J plus R. So again, think of accomplished stages of arrival. Everybody in the system has passed through all R stages. So everybody here is worth basically R stages of service, of arrival. Okay, that's the picture. Great. Next step. Remember, I want to find what? Let's say what we want to find. I'm going to look for the probability in various states, so let's define that. Let's define capital P sub J as the probability there are J arrival stages in the system. In equilibrium. Because that's not what I want. I really want the probability of finding so many customers in a system. So I really want P sub K, don't I? P sub K is our old friend, the probability of K customers in the system. And by the way, what is the system? The system for customers is the Q plus the server. The system for arrivals, Q plus server plus the arrival box, of which is only one person at a time, okay? So how is PK related to PJ? PK is related by adding up a bunch of stages of arrival. And how many are there? You're going to go from J equals RK to J equals R times K plus 1 minus 1 of capital PJ. Let's look at the lower limit, RK. If there are RK stages of service in the system, of arrival in the system, okay, then what's happening? That means there's K customers here, each times R for stages, and nothing more, which means our friend is right here. He's not accomplished anything yet. So that's certainly K in the system. But this guy can go bup, 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 all the way through these R stages. And if nothing happens here, we still have K in the system. That's why the upper limit goes to R times K plus 1 minus 1. Namely, you got the RK for these guys, and you got R minus 1 because this guy is right here. In all those cases, it's exactly K in the system. So that's the way we're going to get PK when we're done. But for now, we're going to start with J, the number of stages. Okay. So what is the next step if I want to find PJ? Yes. Yes.
You said that like from RK to the upper is there's like the guy in the arrival box.
Yes.
Is that the guy who's currently arriving, or is that looking at like the person who could be in the arrival?
No, no. The arrival box is someone arriving. They are not in the system. The guy here, I should use red. The guy here does not count for being here. But little p sub k counts people only in the Q plus server, only in this system here. But that can happen if there's k here and either a person here or here or here or here. Those are the items in this summation. The lower limit means the arriving customer is here. The upper term means the arriving customer is here. He's accomplished R minus 1 stages. That's why it's 1 less than RK plus 1. Again, you know, this is where you can make a mistake if you were doing this yourself. You have to think physically. I mean, in some sense, you're engineers. I know you think of yourself as computer scientists, but you're also engineers. And you have to understand the physics of the problem. Because I'm asking you to do two things. I'm asking you to create the model and then do the analysis. And creating the model is the creative part, in some sense. Doing the analysis is pure mathematics. Get a mathematician. If you can't do it, give it to a mathematician. He'll do it. Okay? But as scientists and engineers, you got to figure out what are the equations you want the mathematician to solve. And by the way, you're also the mathematicians in this class. Okay. But it's important to get, as I say, the physics of the problem. Maybe I'm belaboring that too much, but it's important. Okay. So next step. What do I need to do? I want to find capital Pj and little pk. So what is the next step in this process? I can't give this to a mathematician. By the way, typically mathematicians can't take word problems or diagram problems and create the equations. Some can, they're good. Others are just pure mathematicians. And I love them, they're great. You have a problem, go to them, they'll solve it for you. So we have to make the equations. What are we trying to do next? Quiz problem, yes. Inspection. Write down the equations of motion. Okay, so let's do that. Let's start with this state right here. Let's start with this state right here. That's an easy one, okay? What's the equation for that? 1 in, 1 out, right? So R lambda times P0 out equals basically, how do you get in? At a rate mu from where? I'm sorry, that should be a capital P, by the way. That's a mistake. It should be a capital P. Mu times capital P sub R. Next, let's go to state 1. I'll do this in blue. Okay, what's the state description here? Well, the rate out is only R lambda, so it's R lambda P1. And the rates in are what? In fact, I'm going to do this not only for state 1, I'm going to do for 1 less than or equal to j less than or equal to r minus 1. Because that's the case where people are in the arrival box. So let's call this r sub pj, r lambda pj in this range. Now how can I enter these states? I can come in from below, right, at a rate r lambda pj minus 1. Or I can come in from r states above at a rate mu p j plus r. And now in black, I'm going to take the cases above j equals r minus 1. So I'm going to recognize, if you look at the typical state j I've drawn, the way you leave is r lambda plus mu. So let's write that down. Lambda plus r mu coming out of your state. And the way in, again, is r lambda pj minus 1 plus, from a state above, again, mu p j plus r. And that's basically j greater than or equal to r. Okay. Those are the defining equations. Are there any other equations I need? Yes. Sum of all the probabilities is 1. We'll need that later, but we can't ever forget that or we won't get the problem done, okay? So how am I going to solve these linear difference equations? The way we do is by z-transform. So next step is to form the z-transform, okay? So let's use z-transforms. Which means going to form them, okay? So let me define it first of all. Obviously, the z-transform I'm talking about, p of z, is the summation of all values of j of pj z to the j. And its inverse is, of course, pj, the first thing I want to find, okay? And this is going over all possible states from j equals 0 to infinity, because I can have 0 stages of arrival in the system. We talked about that. That's what this initial state here is. Okay. Now what I want to do, in order to recognize that the blue equation looks like the black equation, almost. So what I'm going to do is the black equation has basically, I'm sorry, I wrote this wrong. This is r lambda plus mu. I'm missing the mu term in the blue equation, the mu pj. So I'm going to add it and subtract it. Because if I add it, then the blue looks like the black, okay? So let's just say that. We're going to add the term mu pj to both sides. Only in the range 1 less than or equal to j less than or equal to r minus 1, okay? Then I can sum. These equations now look the same, except the blue equations will have to give back the pj. Why is this not looking like a j? Okay, so let's do that. So I'm going to get, on the left-hand side, the sum of mu plus r lambda, all of that times pj multiplied by z to the j, and sum now j equals 1 to infinity. Remember, this range over here is only from 1 on up. The zeroth equation is a red equation. But that's not honest, right? I have to give back what I added. I have to give back the mu pj, and I summed over a range from 1 to r minus 1. So give it back. I added it. Now subtract it out. That's going to be minus the sum, j equals 1 to r minus 1, of the mu pj z to the j. Now the left-hand side is basically summing up the red and the blue equations. Right-hand side, the blue and the black look the same, so let's just do that now. I'm going to get a sum over the range from 1 to infinity of what I have here, and the term it looks like r lambda pj minus 1 times z to the j plus the other term, j equals 1 to infinity of mu p j plus r z to the j. Okay. Now I recognize p of z in this, so let's write it down. This leading term in the black equation is clearly, it's got a constant mu plus r lambda. I'll take that out. What's inside is p of z, but not quite. What's missing? The zeroth term. I included in the p of z, so I got to give it back as always. So that's minus p0 times z to the 0, which is 1. Okay. Minus, let's leave this term. I can't fuss with it too much. It's the same thing I have, namely j equals 1 to r minus 1 mu pj z to the j. And on the right-hand side, I'm going to get, well, I need a z to the j minus 1, so take out 1 power of z. So we're going to have r lambda taking that power out. And I'm left with what? The full p of z. Plus now, I need another power of r for z in the last term here. So I got to give it back. So I'm going to have the constant mu giving back the z to the r and putting it in. Sorry. Okay. So what do I have inside? I've got the full p of z, but when j equals 1, basically, I'm missing the term from 0. When j is 1, I'm missing the term from 0 on to up, r. So I got to give back minus the summation pj z to the j equals 0 to r. Now I'm going to play a little game, and then we'll take the break. What I want to do, I want to convert this r to r minus 1 because I've got an r minus 1 in the left side of the equation. And I want to convert this j equals 0 to j equals 1 to j equals 0. Now that means if I go from 1 to 0, I've added a term mu p0. If I go to 0, then I've got to give back basically a term. And what have I added? I've added the mu p0, and up on this right-hand side, I've given back a mu pj. Well, look up here. The red equation is exactly what I've added and subtracted to both sides, so they cancel. I can make these red changes, and that's using the equation, the red equation. Okay, let's solve this now for p of z, and we get the following. And then we'll take the break. I'm also going to multiply by z to the r, and I'm going to get upstairs a 1 minus z to the r And I've got that sum that I didn't get rid of. Namely, it's going from, sorry, it's going now from 0 to r minus 1. Of this mu pj z to the j. That's what's left on upstairs. And downstairs, I'm going to get an r rho. We'll define rho in a moment. Times z to the r plus 1 minus 1 plus r rho z to the r plus 1. See what I've done? I multiply by z to the r by minus z to the r, and I've accumulated things. And I'm going to write this as a numerator over a denominator, and we're going to have to play with that. So, well, lastly, what is rho? Just what you expect. It's basically lambda x bar, as always. And what is x bar in this problem? The average service time? It's pure exponential. It's 1 over mu. So it's lambda over mu. Okay, let's take a break. So I'm fussing around with algebra now. Notice the physics of the problem is gone. Okay? So you better get it right before you start playing around with the equations. Okay, let's take a break. Did this thing ring? Did the alarm ring?
No.
It's interesting. I had it set. Okay. Yes.
I was able to refine my question better.
Sure.
Okay, so is the way to interpret PK as if like, so you like, if you were to pause time and take a snapshot of the system's state, PK would represent the number of people in the system, including the arrival box.
Only in the limit.
Only in the-
You may start it with 1,000 people in the system. The transient has to disappear. If you start the system, as you recall, with that equilibrium distribution, probability so many, PK, started with that probability, it'll stay there.
Okay.
But it's only the people in the queue plus the service.
Okay. Because the reason why I think I'm confused is because the lower limit of that summation is RK, right?
Yes.
And then, so that represents the number of stages completed for the people in the queue and the people in
Arriving.
and people arriving.
But nobody's successfully gone through any stages. If there's exactly K, where's the arriving customer? He's accomplished nothing. He's
He's
in
at
the
zero. He's at
Yeah.
0 stages.
well, no, he's in stage
This is
1.
but he's completed
accompli-
0.
That's right.
Right.
That's
But
right.
So then, RK would be the number of people in the. Oh, because they haven't completed the service stage yet. Like, there's no stages in serve. Okay,
We're not talking about service stage. We're
right,
talking about
I
arrival
was
stages.
confused because I was counting the service as one stage.
No,
So-
no,
right,
no.
right.
That guy there counts for all stages.
Right, because he hasn't completed that. He's
Right.
still there technically.
As soon as he leaves, he
He-
takes all stages with him.
Okay. That makes more sense. Thank you.
Sure. Yes.
I have a question about the solution for the assignment 4.
Yes.
This question why
What is, I forget what the problem is.
the 6th one.
Well, okay, go ahead. I don't remember what it was, but okay. What's the question?
It says they may leave at without service.
Yes, at a rate alpha or with service at a rate mu.
Uh,
They can defect out of the system at a rate alpha.
yeah, and I have a question about why the K.
Because that's how many are in the queue. If there's K in the system, there's 1 in service. How many in the queue? K minus 1. And it's from the queue where you defect. Every one of them could defect at their own rate alpha.
Oh,
So if there's 2 people in the queue, collectively they're defecting at a rate 2 alpha. You alpha and I'm alpha.
oh, yeah. So the people, that means that everyone in the queue will have the
Defect.
Will defect with alpha.
At a rate
Yeah,
alpha.
yeah.
The guy in service won't defect. He'll only be fully served at a rate mu. He's happy. He finally got being served. So the model says that.
Yeah, I got it.
Okay,
Thank you.
sure. I spoke too early. Nobody seemed to complain. I'm being told I got to get this up there also. So we'll start a little early. Just a moment. I don't see that. Oh, there it is. Having trouble putting that on overhead. Let's try it again. Oh, here we go. It's not allowing me to do it. I'll skip it. Okay. So, question is, where are we now? We're going to dive into something interesting, because in order to proceed with that P of Z, what's the next step ordinarily? To do a partial fraction expansion and invert P of Z to get Pj. To do the partial fraction expansion, what do we need? The roots of the denominator, which is the hard part. But we can do something with it. And essentially, first of all, how many roots are there in the denominator? How many roots? R plus 1. It's a polynomial of degree R plus 1. Okay. Can you give me one root of the denominator right now? It's always there. Z equals 1. Some of you sort of missed that on the exam, by the way. But that's okay. So let's identify, first of all, one root at z equals 1. So there's all others, okay? Now, in order to discuss them, I'm going to take you into a deep dive. So just to remind you of that, I'm going to put a red bracket here, and later I'll undo that. I'll finish that bracket, which means that was sort of nasty stuff. But I want to take you through that, okay? We need to show how many of them lie within the absolute value of z less than or equal to 1, and how many greater than 1. That's going to help us considerably. Now, there's one exactly at z equals 1, okay? But there's all others that we have to find, okay? So I want to write, let's write down d of z again. Yeah, kill it. Okay. Let's remember what d of z is. It's shown above. It's r rho z to the r plus 1 minus 1 plus r rho z to the r plus 1. And I want to write that. You don't understand why yet. I want to write it as the sum of two functions, f of z and g of z. And the f's and the g's are as follows. F of z is the minus 1 plus r rho z to the r. And g of z is the rest. It's r rho z to the r plus 1 plus 1. Does anybody have any clue as to why I'm doing this? Have you ever seen this kind of discussion before? Yes?
It's going to be a wild guess, but are you going to try searching for roots of unity?
Search for what?
Roots of unity? Basically, are all the roots less than 1?
No. Well, most of them are. I'm going to use some deep complex variable theory here. And maybe that's what you're referring to. And the particular thing I'm going to do is known as Rouché's theorem. Anybody ever hear of that? Rouchet? You saw his picture the other day. You wondered why? Well, here's why. Okay, it's a very interesting theorem. It's used all the time, by the way, in signal analysis to decide how many roots are in certain parts of the plane. So regardless, I break it into these two functions, okay? Now, for rho less than 1, which is the consideration we want, let's choose any real value, call it delta, such that 0 less than delta less than 1 minus rho, write that more clearly, over r rho. Which means that essentially 0 less than 1 minus rho minus r rho delta. Okay, we're going to need that fact later. Now, in the complex plane, where the values of z occur, and the complex plane is simply the usual, where we have the real part of z on the x-axis and the imaginary part of z on the y-axis. In that complex plane, let's choose a contour. And let's call it capital C. And I'm going to draw it here. It's a contour which is a circle of a particular radius. And the radius is going to be 1 plus delta. Now you have no idea why I'm doing this, most of you, I think. But just stick with me. There's a reason we do. We need this for Rouché's theorem, as you'll see. Okay. So this is the contour C. Right there. Now, on the contour C, the absolute value of z is equal to 1 plus delta. Remember, delta is a real value. So on that contour, which is a constant radius, the constant value of z is exactly the radius 1 plus delta. So we can say the following. The absolute value of f of z, which is equal to the absolute value of what I defined it as, f is minus 1 plus r rho z to the r. Get rid of the, well, let's put the minus in, but we're going to take absolute value. 1 plus r rho z to the r. Which is equal to 1 plus r rho times 1 plus delta to the r, because z is equal to 1 plus delta on the contour. And let's look at g of z. The absolute value of g of z, which by definition is the absolute value of r rho z to the r plus 1, all of that plus 1, that's less than or equal to r rho z to the r rho, not times z, because we know what z is. It's 1 plus delta to the r plus 1. All of that plus 1. In other words, we're taking the absolute value of this thing, because z can be a negative number at some point in there, and it would take away from 1. We're assuming it's always positive, So it's less than equal to what I've written down. Now remember, you don't know why I'm doing any of this. Just live with it, because this is a standard procedure. So on the contour C, the absolute value of f of z minus the absolute value of g of z, which is what I'm after, it turns out, is greater than or equal to 1 plus r rho times 1 plus delta to the r minus r rho 1 plus delta to the r plus 1. And that's because there was an upper bound on z. When I take it away, I get a lower bound. Now this is equal to 1 plus delta to the r times 1 minus r rho delta minus 1. And there's a step or two of algebra there. It's trivial. I won't go through it. If you want, we can. But that's the case. Okay. Now that's greater than or equal to, I'm going to replace 1 plus delta to the r by the first two terms of its Taylor series, namely 1 plus r delta. And the rest I leave as 1 minus r rho delta minus 1. And if you do the calculation there, that's just r delta, take that outside, times 1 minus rho minus r rho delta. And because of what we said above, right here, this quantity is greater than 0. So this whole function is greater than 0. And I went through all that monkeying around because I wanted to show that f of z in absolute value is greater than g of z in absolute value on the contour C. That's why I went through all this calculation. Now, why did I want that? Because there's this famous thing called Rouché's theorem. And it says the following. If f of s, we're using s instead of z now, and g of s are analytic functions of s, inside and on a closed contour, and let's call that contour C, and also if the absolute value of f of s is greater than the absolute value of g of s, looks familiar, on the contour C, then the conclusion, then f of s and f of s plus g of s have the same number of zeros inside C. That's the theorem. Now, what does it mean to be analytic in some region? Basically, if f of s is analytic inside a region, then it basically has a derivative of each point, and in fact is single valued. So Richet's theorem is telling me something about how many zeros there are with f or f plus g. And I've already shown that the f and the g satisfy the condition that the absolute value of f is greater than g on the contour. Okay. Now, I'm going to draw my red bracket. I took you down into the depths. I'm going to take you back out now and take advantage of what I just shown. Okay. Now, you don't have to be able to do this, obviously, but we're now going to take advantage of that. So, I can say, by Richet's theorem, and I could have just said this without showing you what it is, okay? D of z, we know, is equal to f plus g. We defined it that way. We know that that has exactly r roots in the range absolute value of z less than 1 plus delta. Why? Because f, and here's f again, let's pull it up. How many roots does f have? How many roots in this thing? R. And I'm taking advantage of that here because f of z has r roots there. And only r roots. And this is true where? In the range I just described, namely, it's true for all 0 less than delta less than 1 minus rho over r rho, which is the way we defined it. Now, I'm going to let, essentially, delta go to 0. And then we get that the absolute value of z is less than or equal to 1. Because remember, z had the value 1 plus delta right here. You can see it up here. And as delta goes to 0, z in absolute value is less than or equal to 1. But the denominator roots how many are there? There's r in the absolute value of z less than or equal to 1. Of those, we know one of them already. One is at z equals 1. The other r minus 1 are in the absolute value of z less than 1, because there's only one root at z equals 1. So the total number of roots of d of z is, we know, r plus 1 from its definition. I'll go back to its definition up here, right here. We know there's r plus 1 roots for d of z. Total numbers, let's see what we've learned now. We've got d of z has basically r minus 1 roots in the absolute value of z less than 1. It has one root at z equals 1, and one root elsewhere, which means absolute value of z greater than 1. So that was the whole point of diving into Richet's theorem, to be able to say where the roots are and how many there are. Okay. Now, we have one other funny thing in our expression for P of z. Remember, we're trying to invert P of z. If you look P of z in this expression here, we got this funny thing here. And we don't know those pj's. At the moment, they're unknown. And how many are there? There are of them. Okay? So it's got r unknowns. Let's say that. The numerator of z has r unknown values of pj. We got to find them also. Okay. Now remember also that the z transform of a probability distribution, this was basically on your exam, must be analytic in z less than 1. Why? Well, what is a z transform? It looks like this. Summation, say, of a probability distribution, z to the j. As long as z is less than 1 in absolute value, an upper bound on this is sum of the pj's. And the sum of the pj's is 1. So it can't blow up, okay? Can't blow up. And we needed that for one of the, remember we looked for capital A and capital B in one of the problems in the exam. And I told you this fact there. And you'll see when you redo it why you needed that. Okay. So basically, P of z must be bounded in this region, in z less than 1. And here's the hooker. Since d of z has r minus 1 roots there, in the range z absolute value less than 1, what can I conclude? P of z can't blow up in this region, z less than 1, but the denominator is going to 0 in that region. If the denominator goes 0, it blows up. So what is this telling me? If the denominator is going to 0 there, numerator must be going to 0 there to cancel those zeros. And that's going to tell me what these unknown pj's are. They give me the opportunity to cancel those zeros as follows. And by the way, it must have roots in those same points where the denominator does. So it must P of z. So let's say this specifically. The numerator must have zeros at the same r minus 1 points. That the denominator does, okay? Now let's write down the numerator again. I'll go back to P of z, somewhere here. The numerator is this baby. So let's write it down. Numerator is 1 minus z to the r times that funny summation that we were left over with. Namely, j equals 0 to r minus 1 of pj z to the j. Now, where are the zeros of that term? Zeros in absolute value of z equal to 1. That means that the rest of this, that's where the r minus 1 bad zeros have to be matched to eliminate them in the denominator, or else the thing would blow up. So let's say that. How many roots are there of this sum? Well, it's of degree r, okay, r minus 1, I mean. So basically, these r minus 1 zeros must match the denominator zeros. For, again, absolute value of z less than 1. So what I'm basically saying is n of z must match d of z after 2 roots of the denominator taken away. If you will, are factored out. What are those 2 roots? Come back to the summary here. It's these 2. Take them away, factor that out of the denominator. What's left better match that numerator. Okay? So let me say what those roots are. It's z equals 1, and I'm going to name the other one. Let's call it z0. z0 is the root that's greater than 1 in absolute value. So let's say that. I've got d of z. Let's factor out those 2 roots. 1 minus z, 1 minus z over z0. What's left are the bad roots, the r minus 1 bad roots. And they got to be matched with the numerator. So it's got to be equal to, and by the way, it's not going to be matched by these red things, because they all hit at 1. So it's the blue thing that's got to match it with some unknown constant, let's say k times that sum. K times that sum from j equals 0 to r minus 1 of pj z to the j. Now, and we're going to find k later, but this is telling me what that nasty little sum is all about. These r minus 1 roots are going to cancel out the r minus 1 unknown pj's. So let's make the next obvious step. P of z, which is equal to n of z over d of z, is equal to, let's write down what it was before we do anything to it. It was this thing. It was 1 minus z to the r times that sum from j equals 0 to r minus 1 pj z to the j over that denominator, which remember is r rho z to the r plus 1 minus 1 plus r rho z to the r, all of that plus 1. But we know from this equation at the top of the screen, d of z itself is equal to 1 minus z to the r. I'm sorry. From the equation of 1 minus z, not z to the r. Sorry. It's this thing here. 1 minus z times 1 minus z over z0 times k times that sum that we're trying to get rid of. Now, put this equation at the bottom of the page in the denominator of the line above. And what are going to get? That p of z is equal to, the 1 minus z to the r stays there. I didn't mess with that. And downstairs, this whole thing, this whole denominator, is basically going to be this sum. Let me circle it. This sum is going to cancel that sum. And so what I'm left with is k, I don't know what that is yet, times those two roots, a 1 minus z and a 1 minus z over z0. Wow! Look how simple that is. All those r minus 1 roots that gave me trouble disappeared. They had to be matched with the numerator sum. I never had to find them. They're gone. Okay? Now to get k, let's remember our good old friend we talked about before. P of 1 equals how much? One. And let's plug that in, okay? That says basically that 1 is equal to, let's write down what it is. Well, let's see. If I put z equal to 1 in P of z, it's 0 over 0, isn't it? L'Hopital, our good friend with the hair, okay? So let's do that differentiation. Numerator and denominator separately. Upstairs, I get a minus r z to the r minus 1. And downstairs, I'm going to take the k outside for the minute. And inside, I get a minus 1 times a 1 minus z over z0 plus a term I'm going to get rid of. It's plus a 1 minus z times a minus 1 over z0. But, of course, now I'm going to set z equal to 1. Let me move this over. All of this at z equals 1. So this last term downstairs will disappear. And I simply get that 1 is equal to minus r upstairs. And I'm going to multiply by minus 1. So I'm going to get an r over k times 1 minus z over z0. So basically, I got rid of this minus sign right there. Okay. That gives me that k is equal to r over 1 minus z0. 1 minus 1 over z0. So let's go back to P of z now. So P of z is equal to, remember what we have up here, it's got a k downstairs and all the rest of it upstairs. So let's write that out. The 1 minus z to the r stays there. This 1 minus 1 over z0 downstairs goes upstairs. 1 minus 1 over z0. And downstairs I get an r times 1 minus z, 1 minus z over z0. And now we're almost ready to do the inverse. We call it partial fraction expansion. Can I do a partial fraction expansion on that equation? Why not? Degree is wrong, right. Numerator degree is much bigger than the denominator degree. It's got to be less than the denominator degree. But there's also another fact I can use. Z to the r behaves nicely in transform domain, basically. Okay, let's remember that if some function called f of z has as transform f sub n, then z to the r times that f of z is what? It's f of n minus r. That's one of the properties we have. How nice. So I can take this 1 minus z to the r outside, work with all that's left, and play the game at the bottom of the page. So let's do that, okay? So the partial fraction expansion will give me the following, okay? It's going to give me p of z equals, and let's take that nasty term, the 1 minus z to the r, outside for the moment, and we'll use this fact about the shifting in time. And when I do a partial fraction expansion on the rest of this, what am I going to get? Well, let's see, I'm going to get a 1 minus z term and a 1 minus z over z0 term. And I'll have a 1 over r. So I'm going to get the following. I'm going to get a 1 over r over 1 minus z plus a minus 1 over rz0 over 1 minus z over z0. Now I'm ready to do the inverse. Let's focus on this thing, and let's call its inverse f sub j. I'm using arbitrary notation f right here. Let's invert that, because once it's done, I can play this game up here. I'll get two terms out of it, okay? So, if I do that, I'm going to find that p, let me do it in black. If I do find the inverse fj, then pj will be fj minus fj minus how much? Instead of z to the r, instead of z to the n, I have z to the r, so that's exactly right. So it's minus r here. So just find little f, and you have the answer. So what is little f sub j? You can invert this bracket easily. It's a 1 over r comes out times the first thing gives me. What does this term give me when I invert it? 1 to the j, which is 1. Okay? So it's simply a 1. Minus the other thing, and I'm going to get essentially a 1 over z0 to the j. I'm going to get that. Times, and that's the power term, and I had to put one of those outside. In other words, it's 1 over r times 1 minus z0 to the minus j minus 1. Now let's use that and the thing at the top of the page to get finally pj. Okay. Let's first of all find pj in the range j greater than or equal to r, because, you know, if j is less than r up here, then I get a negative subscript, which means that doesn't exist. So let's first of all put it where it does exist, okay? Then I'm going to get Pj is equal to the thing I just found for Fj, namely it's 1 over r times 1 minus z0 to the minus j minus 1. Then I can subtract from that this other term here, this guy right here. So I'm going to subtract off a term which is 1 minus z to the minus j, take a minus r, minus 1. Let me move this over. Okay. Excuse me? I don't understand. I'm saying it again. You're correct. You're correct. Because it was a minus r. Exactly right. That should be a plus right here. Thank you. And there's a paren around here. Okay. So that means that Pj is equal to 1 over r, and take outside z0 to the r minus j minus 1, and all of that times 1 minus z0 to the minus r. And that's for j greater than or equal to r. Now, before we take the term less than that, let's monkey around with this a little bit, okay? Remember that d of z is equal to r rho z to the r plus 1 minus 1 plus r rho z to the r plus 1. That's what it was originally. But d of z at z equals z0 is how big? 0. It's a 0 of the denominator. So that's 0. So let's plug that in. That implies the following, that r rho z0 to the r plus 1, z0 to the r plus 1, must equal this other term, namely 1 plus r rho z0 to the r minus 1. Multiplying that by z to the minus r, we'll get that r rho times z0 minus 1 is equal to 1 minus z0 to the minus r. And I went through all of this because I wanted to replace this term with this term. That means that Pj is equal to the 1 over r, and I got the z0 to the r minus j minus 1. In place of the 1 minus z0 to minus r, I'm going to put the new thing I just cooked up, which is r rho z0 minus 1. And that's for j greater than or equal to r. Now, for 0 less than or equal to j less than r, f sub j minus r is 0. Doesn't exist. So finally, I get the expression. The final, or near final, is the following. Pj is the following. It's what I just cooked up. It's 1 over r times 1 minus, and put the z0, multiply the z0 through this, and I get a 1 minus z0 to the minus j minus 1 for 0 less than j, less than equal to j, less than r, or the thing I had before, which is rho, because I'm going to multiply. The r's cancel up here. These two r's cancel. I'm going to get rho z0 minus 1 times z0 to the r minus j minus 1. And that's for j greater than or equal to r. Almost done. What's the other step I need? I didn't want j. Those are the stages of arrival. I want the number of customers. So let's do our friend. Let's use what we said before, namely p sub k is the summation of these pj's from j equals kr up to r times k plus 1 minus 1. And you can do a little bit of algebra. I can show it to you, but you're going to end up summing a geometric series and using our old rule for that. I finally get that pk. The thing I'm really looking for is the following. It's 1 minus rho for k equals 0, and it's equal to rho times z0 to the r minus 1 z0 to the minus rk for k greater than or equal to 1. That is our answer, ladies and gentlemen. It's a very simple answer through a fairly complicated analysis. And notice that it's a geometric distribution. Not a sum of geometrics like for MER. It's a simple geometric. And all you need is the root z0 of the denominator greater than 1. So all you got to do is find one root, and you've got MER1. After all that monkeying around with Boucher's theorem and all the rest. I took you down there to show you how we get here, but that's a beautiful answer. We're going to derive it more directly when we get to chapter 6, I believe. Okay. Now, any questions about this? I took you through a deep dive, and I know it's probably confusing you, because if you haven't seen the complex variable theory, this is new to you. I want to let you know there's a basis for it. And these mathematicians use these complex variable theorems all the time. Question? When z is 0?
Are we going to find z0 to yield k, or is it going to be given to us?
You've got to look for the root of the denominator. Where is it again? You got to look for the root of this thing, but only search for it. It's always hard, but you don't have to find those for less than 1. You want to find the one which is greater than 1 in absolute value. You could do it numerically. You can try to do it analytically, depending upon what the functions look like, what R looks like in particular. But the fact that it's simply a geometric is very nice. Now, was there other questions? I see one smiling face, a lot of glum faces, and some bewildered faces. Yes?
Is z0 guaranteed to be a real number? Because from the formula it seems like it's a real number.
It will be a real number. And that's a very good observation, because otherwise these PKs wouldn't make any sense. You're quite correct. So it makes the search a little easier, too. Now, while we're at it, any other questions? Let's check this for MM1. It's always a good check to see how we're doing. In that case, R equals 1. Okay? So what we have to do is, what is the answer for MM1, by the way? We know that PK is 1 minus rho to the k. You've memorized that. Let's prove it now, okay? We need the following. We need R rho times Z0 minus 1 to equal 1 minus Z0 to the minus R. That was the condition we had above. Well, R is 1, so we get rho times Z0 minus 1 should equal 1 minus 1 over Z0. Multiply through by Z0, you get rho Z0 times Z0 minus 1 equals Z0 minus 1. So what does that say? Immediately, what is Z0? Come on, look. This kills that, right? So Z0 is 1 over rho, exactly. Okay, so let's put that in to our equation above. So PK is equal to rho times Z0 to the R, Z0 to the 1 over rho to the 1 is in fact 1 over rho, minus the 1 in the expression. And it's 1 over rho, that's a Z0, to the minus RK, which is minus K. And that's equal to 1 minus rho to the K, sure. That was a trivial case. And we found Z0 rather easily. Okay. Took a long time to do. Took us almost a full 2 hours to do MER1, M1. The answer is simpler than MER. MER was a summer geometric. This is a single geometric. Okay, now a little observation. Let's come back to something we did much earlier. Let's look at MER1. When a customer comes in, what does he bring in with him or her? R stages of service. And then we followed through and we got our answer. That's as if every time a customer comes in, he brings in R things. Suppose we thought of that as as soon as an arrival comes, it's a bulk of size R. In this model, it's a bulk of R stages. But suppose it was a bulk of R customers. So we're almost modeling a bulk arrival system with exponential inter-arrival times and exponential services. And so we can use the technique we use for this to solve bulk arrival. The nature of the bulk here is all bulks are the same size, size R. Well, I want to be more generous than that. I want to solve it with a distribution of bulk size. You could have 1, 2, 3, 5, 10, 100, a million. Okay? So since we have a little bit of time to do that, let's set it up. Okay. So what I want to do now is a bulk arrival system. Again, the system you've seen above there, let me just copy that diagram. In fact, let me copy the, here's the state diagram. Let me copy that. This will describe a bulk arrival system where all the bulks are the same size. Except, and they're coming in at a rate lambda, bulks of size r. So when a customer comes in, they move from none to r. But instead of stages, think of it as customers. But what's wrong with these labels? Remember, I'm trying to describe an M1 system with bulks of size r. So this diagram is not quite correct. The labels are wrong. What's wrong? They're not being served at a rate r mu. They're being served at a rate mu. So I simply have to change all of these to mu. And now I got a bulk arrival system where the bulks are fixed size r. That means we can use the P of z we got by changing r mu to mu and the pj's, and we'll get done. But as I said, let's be more generous now. So again, the MER system solves this if it's fixed size bulk. But let's be more generous. And allow basically random size bulks. Namely, I'm going to let G sub I equal the probability that the bulk size is I. Is a probability size 1, size 2, size 3, size r, so anything. Okay? And the bulks arrive from a Poisson process. Namely exponential interarrival times. At a rate lambda, just like in our usual systems. And as we usually like to do, let the state variable be number of customers in the system. Not stages, but customers. Okay. Let's draw the state diagram. It's fairly complicated, so I'm going to focus basically on the state k. And I'll look at k minus 1. I'll look at k plus 1. I'll look at k plus 2. And even k minus 2. And of course, this goes on up above and comes in from below. Okay, now, when I'm in state k, how can I leave it? There are k customers in the system. It's an MM1 bulk arrival. If I get a service, where do I go from k? If somebody leaves service? From k to where? One customer leaves. You've dropped down by 1, right? And what's the rate of that? A good friend mu. That means I can enter state k from k plus 1 with the same idea at a rate mu. Now, how do I enter state k besides from above? Well, that could have been a bulk arrival. For example, if there were k minus 1 in the system, and somebody arrives and the bulk size is 1, then I'll move this way. And what's the probability, what's the rate at which I get bulks of size 1? At rate lambda, they're coming in. Oops. And with probability G1, the bulk size is 1. I could have come there from state k minus 2 if the bulk size was 2. That happens at the rate lambda G2. And in general, I can come from any lower state. Whoops, wrong one. Coming from any lower state at a rate lambda sub GI, say from state I, below it. Moreover, from state K, I can get an arrival before there's a departure, and at a rate lambda G1, I go to K plus 1. At a rate lambda G2, I can go to state K plus 2. And I can go a whole bunch of other places. Let's call that lambda GI. Then I go to state K plus I. And we have all these mu's coming down, etc. So let's look at and ask ourselves, what's the rate of leaving state K? Well, I could have a service at a rate mu, or could have come at an arrival at rate lambda and go to the next state up J1, or same rate lambda times G2 plus dot dot dot. But that's simply equal to mu plus lambda summation of all the GIs from 1 to infinity. And what is that sum? That sum is just 1. By the way, you can have a 0 bulk also. I can make G0 could exist as well. I'll include it later as we like. Okay. Now I want pk that's the equilibrium probability of finding k in system, as always. Okay, next step. I've done the physics. Now I need equations. What equations am I looking for? The balance equations, using what technique, Matt? Right, you didn't even know the question, but you knew the answer, right? Right. Okay, so we're going to use inspection method, and we're going to write down the system equations. We're going to use Z transform to solve it, and we'll be done. And we will have solved a rather interesting bulk arrival system, and that we hold off for, we have a class this Friday, don't we? But no class Monday, that's President's holiday. Please make sure I'm saying that correctly. We have a class on Friday. No class Monday. You forgot that. I forgot it too. But no class Monday. Okay. Very good. I'm going to assign the exam as homework I'm going to put up there tonight. And it'll be due Sunday night. It gives you the weekend to work on it. Okay.